evaluate integral over c z minus 3 into dz upon z square plus 2z plus 5, where c is the circle, modulus of z equals 1, modulus of z plus 1, minus I equals 2, modulus of z plus 1 plus I equals 2. If you consider f of z equals z minus 3 upon z square plus 2z plus 5, we have poles obtained by equating denominator to 0. When you solve the quadratic equation z square plus 2z plus 5 equals 0, you obtain the poles as z equals negative 2 plus minus root of 4 minus 20 upon 2, which after simplification becomes z equals minus 1 plus minus 2i. In the first circle, modulus of z equals 1, centered at origin and radius equals 1, we have pole z equals minus 1, minus 2i has x equals minus 1 and y equals minus 2, whose modulus is root of minus 1 the whole square plus minus 2 the whole square, which is root of 1 plus 4, which is root 5, strictly greater than 1. Therefore, the pole z equals minus 1, minus 2i lie outside modulus of z equals 1. Similarly, the pole z equals minus 1 plus 2i has modulus z equals root of minus 1 the whole square plus 2 square, which is root 5, again strictly greater than 1. Therefore, the second pole also lie outside modulus of z equals 1. Since both pole lie outside C, by Cauchy's theorem we have integral over Cf of z dz equals 0. When you consider the second circle, modulus of z minus I minus 1 equals 2. The first pole z1 equals minus 1 plus 2i, whose modulus when evaluated in this expression, we have modulus of z1 minus I minus 1 when evaluated gives us modulus I, which is strictly less than 2. Therefore, z1 lie inside C. When you consider z2 equals minus 1 minus 2i, which is the second pole, when you substitute z equals z2 and evaluate the modulus in this equation, modulus of z minus I minus 1, when you evaluate the LHS, we have modulus obtained as modulus negative 3i, which is strictly greater than 2. Therefore, pole z2 equals minus 1 minus 2i lie outside the given circle C. In order to evaluate integral over Cf of z dz, it's enough to evaluate residue corresponding to z equals z1, which lies inside C. We have integral over Cf of z dz equals 2 pi I times residue of f of z at z equals z1. To evaluate residue, we have the formula limit z tends to z1 applied on z minus z1 into f of z. When you cancel z minus z1 from both numerator and denominator, we have the expression 2 pi I times limit z tends to z1 applied on z minus 3 upon z minus z2. Directly we can apply z equals z1 in the expression z minus 3 upon z minus z2. After simplification, we obtain integral over C f of z dz equals 2 pi minus 2 plus I. In the third circle, modulus of z minus 1 minus I equals 2. We have center given by minus 1 and radius equals 2. When you consider the first pole z1 equals minus 1 plus 2i, when you evaluate modulus z1 minus 1 minus I, you obtain modulus value modulus 3i, which is strictly greater than 2. Therefore, pole z1 lie outside the given circle C. When you consider the second pole z2 equals minus 1 minus 2i and evaluate the modulus in this equation in the LHS, we have modulus value obtained as negative I, whose modulus is less than 2. Therefore, z2 lies inside C. It's enough to evaluate residue corresponding to z equals z2 for the f of z given, and we have integral over C f of z dz equals 2 pi I times residue of f of z at z equals z2. We have integral over C f of z dz equals 2 pi I times limit z tends to z2 z minus z2 into f of z. Cancelling z minus z2 from both numerator and denominator, our expression reduces to 2 pi I times limit z tends to z2 z minus 3 upon z minus z1. Directly applying z equals z2, we have the expression reduces to pi times 2 plus I. Therefore, integral over C f of z dz equals pi times 2 plus I.